everybody, and welcome to our last unit in acid bases, which is all about titrations. Now, I know you've titrated already. We've titrated in that redox titration. You did that virtual titration, and I feel like we've definitely done it again at some point. But we are going to really break down titrations because these are especially important when we're trying to determine what is the concentration of an unknown acid or a base. And there's a lot of chemistry that goes into how the pH changes as we progress throughout a titration. So, of course, acid-base reactions can be carried out under these controlled conditions, which is called a titration. And you've seen a titration before. So here's an example of what it looks like. We have some solution, and this is acid, but it could also be a base. It depends what you're titrating and what is in the burette. This right here usually is what we call the analyte. And the analyte is what we're trying to measure, usually. Not always, but sometimes it is. So a lot of times you're going to have something that you're measuring in the beaker. And you're going to add to that what's known as an indicator. So you've seen a little bit with indicators before, but what we want to do, and we'll talk about how to choose an indicator sometime in this video, but you want to select some sort of indicator. So we'll select an indicator that changes at the desired pH. So you want some indicator that's going to be most useful for your particular reaction. If you know that your reaction is going to occur at a pH of about, I'm just making this up, 4, you want to use an indicator that also changes at about a pH of 4. And that's when you know you've reached the end point of that, or the equivalence point of that particular reaction. And we're going to talk a little bit more about what that means later in this video. So I have my analyte, whatever is being measured. I have some indicator that I add to that. This right here typically is what we call the titrant. And the titrant a lot of time has a known volume because you can measure, of course, how much you're adding, and it has a known concentration. Now, when you're standardizing, that's a little bit different because when you're standardizing a solution, a lot of times you don't know the concentration of what's in the burette. However, for usual acid-base reactions, other than a standardization, you would know the concentration of this and we would know the volume. So of course, I would have my unknown amounts down here with my indicator. I would open the stopcock and I would release some of that liquid, as you could see, and that volume is going to go down. So we could see the change in volume right there. Then we have our final reading. We know that this reaction is done when the indicator has changed color. So we see there that we chose an indicator that will signal to us when the reaction is over. And typically that's when your moles of acid is equal to your moles of base. And because we could signal that and we can measure how much of this particular solution we added with a known concentration, we could figure out what is the concentration or what is the mass of liquid in this or the mass of acid in this particular sample. So there's a lot of really good chemistry that we could do with titrations, and we're going to talk more about these throughout this video. And what we could do with titrations is we could plot how the pH changes as we go through a particular titration. So in this particular image, we see how the pH is changing as I add some 0.100 molar sodium hydroxide to 50 milliliters of 0.100 molar hydrochloric acid. So this, as we know, is a strong base, and this, as we know, is a strong acid. If we were to consider the net ionic equation for this, so of course your sodium is a spectator and your chloride is a spectator, we have hydrogen ions react with hydroxide ions to produce water. So if I have two solutions that have the same exact concentration, we'll see that the pH is not going to change very much at first. And that's because you don't have nearly enough hydroxide ions in there to start neutralizing that acid. What's going to happen though, so look, it starts to go up very, very quickly. There's a point at which the number of acid molecules or the number of hydroxides is equal to the number of hydronium ions. And this right here is what we call our equivalence point. And notice our equivalence point between a strong acid and a strong base is right at 7. So this is a totally neutral solution when I have a strong acid and a strong base. You can also consider, all right, well, how much of that base did I need to reach that equivalence point? And if I look down this graph, it looks like I needed 50 milliliters of that hydroxide to totally neutralize that acid. And that makes sense because both of these, this hydrochloric and this sodium hydroxide, have the same concentration, and it's a 1-to-1 mole ratio. Of course, I would need 50 milliliters of the base to neutralize 50 milliliters of the acid. So there's a lot of really good stuff that you can tell from a particular titration curve. So let me get rid of the pen here, and I want to type actually what some of these definitions mean. So you've heard me talk about the equivalence point a couple of times already. But what the equivalence point is it's when the number of moles of acid is equal to the number of moles of the base. And this is really one of the most, if not the most important part of a titration, is your equivalence point. And you'll know that you've met your equivalence point when you can find this line that goes straight up and down when your pH is changing drastically. Normally it's right in the middle of that line is your equivalence point. And that's when your number of moles of acid is equal to your number of moles of base. And typically that's when the reaction is over. That's when you have a stoichiometric equal amount of acid and base that's there at your equivalence point. However, what an indicator does is an indicator measures where our end point is, which normally the end point is sort of where the equivalence point is. The end point is the point at which the reaction is over. And normally this is indicated by a color change. And we've used the pH meters once or twice by this point. I am not a fan of pH meters are great, don't get me wrong, but they're such a pain in the neck to stabilize and to calibrate, especially the ones that we have, and they're very expensive, the ones that you hook into the computer. So pH meters are best. So we'll say pH meters work best for this. But we could also use indicators. And that's because they're more convenient. I have a ton of indicators in the back, and these will typically signal when we've reached the end point of a titration. So it's when the reaction is totally over. So you always want to choose an indicator that changes color at the desired pH. So it says down here, when we're doing a titration, we typically use phenolphthalein, and that's because we are titrating with either a strong acid or a strong base, or usually a weak acid with a strong base. A lot of times that particular reaction will have its equivalence point at around 8. And that's why phenolphthalein is so prevalent when we are doing titrations, because phenolphthalein changes at a pH of around 8, which is normally where we want to signal that the reaction is over. You can also use something like Cresol Red. Cresol Red turns at about a pH of 7, which is more neutral. You could also use bromothymol blue, which I'm sure you've used in AP Bio or in some of your biology classes. That, I believe, tends to change at a much lower pH. I want to say around 3 or 4. So they signal at all different pHs. The universal indicator, which you saw, changes throughout the whole entire range of the pH spectrum, which is kind of cool. Let's take a look at here. So what's present in the beaker as we go through this particular titration? So it says, using the sample titration curve below, determine the species present at each point by filling in the beakers. So we can tell just by looking at this graph that I am reacting a strong acid with a strong base. And I could tell because my pH is very low to start off with. So I know this has to be a strong acid. And because my pH ends up relatively high, a little bit higher than 1, we could say that I'm reacting this with a strong base. So where that pH starts and ends up is a good indicator of what type of acid or base we're using, whether or not it's strong or weak. So at each particular part of this, now we can consider the net ionic equation for this because of course it would be hydrogen ions react with hydroxide ions, and that produces some water that's there, our net ionic equation. If I'm at point A, so at point A, I have hydrochloric acid only, right? So here in my beaker, I would only have hydrogen ions, but I would also have some chloride ions. Those chloride ions are spectators, and we have to remember that they're still going to be there in the beaker, even though we're not reacting with those. So I'm just going to draw some particles in here. I'm going to draw 3 of each because we want to make sure that we have an equal number of hydrogens to an equal number of chloride ions. That's all that's in the beaker at A, and that's because I really didn't add much base yet at this point. So if I look on my x-axis here, I might have added 1 milliliter of base, if any at all. However, as I add more base, so as I go across my x-axis here, you'll see that my pH really isn't changing too much. And that's not because I'm at a buffer. That's just because I have a lot more acid than I do base. But at this point, we're going to see that I am adding some of this sodium hydroxide. So we'll say our strong base is sodium hydroxide in this case. Just makes life a little bit easier to consider always hydrochloric and sodium chloride. Or I'm sorry, hydrochloric and sodium hydroxide. Once I start adding some sodium hydroxide to this particular solution, those hydroxide ions are going to react with some of your hydrogen ions, right? Because they're going to form water. However, I still have a very acidic solution at this point. So I'm going to draw maybe 2 hydrogen ions that are present, because one of those hydrogen ions might have reacted already because it reacted with the hydroxide, because I did add some base to this already. I still have all those chlorides. All those chlorides are still present because they're not going anywhere. They're just spectating. However, if you look at this beaker, you'll notice that the sum of your charges doesn't equal 0. So I have some hydrogen ions. I have 2 positively charged ions and 3 negatively charged ions. Where's the other positively charged ion? You have to consider your spectators. So this is my other sodium ion that's coming in. Why a sodium ion? Because if one hydroxide ion reacted with one hydrogen ion, let's say one of those goes away, I now have a sodium ion that took its place. So at this point in the titration curve, I would still have hydrogen ions because it's still acidic, although less hydrogen ions. I would still have all my chlorides, and I would have a couple of sodiums, though not very many. Once I reach C is my equivalence point. So notice how it's right in the middle of this vertical line. And you'll see that C has a pH of 7. So that means that this solution is neutral. So that means I have an equal number of acid as I have to base. So if all of this acid has reacted, that means I have no acid left. In fact, I started to add more hydroxide to this. In order to have a neutral solution, and you consider this particle diagram, how many of those hydroxides should I have added? Well, probably 2 to get rid of this guy and to get rid of that guy. So I'm not going to have any hydrogen ions left in the beaker, but I'm also not going to have any hydroxides left in the beaker, and that's because they're totally neutral. They've canceled each other out. We've produced all the water we could at this point. What's present in the beaker? I have chloride ions, but I also have 3 sodium ions. Why 3 sodium ions? Well, because if I added 3 hydroxides to react with all 3 of these hydrogens, that must mean I added some spectators in there as well. This right here is a neutral salt, right? It has a pH of 7. It's got no more acid than it has base. All that's present at the equivalence point is just your spectator ions. We're eliminating water just to kind of make this a little bit easier to read, but you would in fact have some water molecules in there as well. Once I get to D, so D is where I have a lot more base than I have acid, and we know that because my pH is very high in this case. So if I just keep adding more base to this, once I get past the equivalence point and I keep adding base, I'm still going to have all of these spectators. So I still have a sodium, I have another sodium, here's another sodium. I still have my 3 chlorides present. But if I went past that equivalence point, now I have more base that's present. So if I have more base, I'm going to add some base in there. However many bases that I add hydroxides, I must also add that many sodium ions, because remember, they're spectators. We have to also consider that when we're drawing these particle diagrams, that the number of particles is very important, and that's because the charge of this whole entire system has to always be neutral at all times. Now, of course, you might not always include spectator ions, and that's okay. But in this case, I wanted to show you that those spectators are in there the whole entire time. So at part C, you would have your spectators, sodium and chloride. But because your base is in excess at this point, you would also have those hydroxide ions. This is what a titration typically would look like when you react a strong acid with a strong base. So in this case, your strong base would be the titrant. This would be what's in the burette. You're adding that slowly, drop by drop. And your hydrochloric would be your analyte. This would be present down in the flask, down at the bottom. So this would be your hydrochloric, and you would have your sodium hydroxide in the burette. Let's consider reactions with strong acids and strong bases. So by doing some stoichiometry with them, which we've already done, but let's do a couple just because it's always nice to refresh our memories. So if 25 milliliters of 0.75 molar sulfuric acid is required to neutralize 0.427 molar potassium hydroxide, what volume of potassium hydroxide was used? So in this case, we do have to do a little bit of stoichiometry, but it is important to write an equation out. And that's because if you notice, this is not a 1-to-1 ratio, actually. So I have sulfuric acid, strong acid, reacts with a strong base, which is potassium hydroxide. We're going to form potassium sulfate and water. Remember, these are your spectators. So sulfate's a spectator, potassium's a spectator. But if you were to write, or if we were to balance this rather, looks like I have 2 of those. I need to throw a 2 there. And looks like I need a 2 here. So my mole ratio of sulfuric acid to potassium hydroxide is 1-to-2. And I have to consider that when we do our stoichiometry. So I'm going to start off with 25 milliliters of the sulfuric. 1,000 milliliters is equal to 1 liter. It's not a very straight line, but that's okay. 1 liter of sulfuric contains 0.75 moles of sulfuric. And it looks like, according to my balanced chemical equation, 1 mole of sulfuric acid reacts with 2 moles of potassium hydroxide. So you do have to check that balanced chemical equation. 98% of the time it's going to be 1-to-1, but it is always important to recognize if it's not 1-to-1. Let's use our concentration for the potassium hydroxide. Looks like there are 0.427 moles of KOH in 1 liter. And 1 liter contains 1,000 milliliters. So if you solve for this correctly, you should find that there are 87.8 milliliters of potassium hydroxide that would have been neutralized. Right there. It's an 87.8. It looks kind of sloppy, but that's what it's supposed to read. So in order to neutralize 25 milliliters of 0.75 molar sulfuric acid, you would need to add 87.8 milliliters of 0.427 molar potassium hydroxide. Let's write an equation for the next one before we even get started, just to make sure it is a 1-to-1 ratio problem. So my nitric acid and my lithium hydroxide, both strong, produces lithium nitrate and water. And it does in fact look like this is all 1-to-1. So I could just move on and do the work as I need to. So 15 milliliters is mixed with 25 mils of this. Calculate the molarity of nitric acid. I usually like to calculate molarity of this because we have to remember that molarity is equal to your moles per liter. And you are actually already given the volume of this nitric acid. So we know this liter on the bottom. We know it's 0.0150 liters. To find the molarity, we need to know how many moles of nitric acid has reacted. So to do that, we are going to figure out, based on our other values, how many moles of nitric acid did in fact react with 25 milliliters of the 1.5 molar lithium hydroxide. So to do that, let's start with our 25 milliliters of the lithium hydroxide. 1,000 milliliters is equivalent to 1 liter. 1 liter of lithium hydroxide contains 0.150 moles of lithium hydroxide. Now let's figure out, using our mole ratio, how many moles of nitric is going to react with that, because according to my mole ratio, 1 mole of lithium hydroxide reacts with 1 mole of nitric acid. And this will give you a value of 0.0375 moles of nitric. And now you have that top numerator in that molarity equation. So to find the concentration, there are 0.0375 moles of nitric. And if I titrated, if I use 15 milliliters, so again, that's my 0.0150 liters of nitric solution, I get a molarity of 2.50. So it's always important to really consider those units. And the more practice you get with these, the better you will get. So if you don't do those book problems will help you to kind of see how to do these reactions, because there's so many different ways that you could do them. This is all the work for when I react strong acids with strong bases. However, what happens when I introduce a weak acid with a strong base, or a weak base with a strong acid? Our titration curve looks a little different. So you'll notice here that it's a little bit more curvy in this case. And one way to tell that you're titrating a weak acid with a strong base is by looking at the starting points, like we said. So we'll notice here we have a slightly higher pH. And this slightly higher pH tends to tell us that this must be a weak acid, because weak acids tend to have slightly higher pHs, of course, because they don't fully dissociate. And then we'll see that we do have a very nice area where you'll see this buffer region. So as I'm adding base, as I'm adding strong base, you'll see that the pH is changing, but it's not changing very much as I keep adding. That's my buffer region. So if I look here at this strong acid, I don't have a buffer region. I just have the pH is relatively constant until, it changes very quick. And then it gets to its new pH. This one, you'll see it has this little bit of a curve, and that's because that weak acid is a buffer, right? If I add some of that conjugate base, that's resisting that change in the pH. So you're going to see a curve that looks a little more like this. Let's talk about this buffer region. So let's pull this out again. And your buffer region is the region where there is very little change in pH, which you can clearly see by looking at this image. So what I'm going to do is I'm just going to highlight this buffer region. So the buffer region right here is this whole entire section right there. That's our buffer zone. And you'll notice that we also have an equivalence point, just like we did with the last one. So if you find that point where this vertical line goes up, your equivalence point is going to be somewhere in the middle. So we're going to look here. Here's our equivalence point. Equivalence point. And you'll see that the pH is actually higher than 7 at the equivalence point, which is interesting. However, with weak acids in a titration, we can also consider the half equivalence point. And your half equivalence point is going to be in the middle of the buffer region. So the half equivalence point is where, or is the point where half of the weak acid has reacted, which makes sense. If the full equivalence point, what we talked about previously, is when your moles of acid equals moles of base, the half equivalence point would make sense that it's where half the acid has reacted. And at the half equivalence point, it is very important to know that the pH of the solution is equal to the pKa of that solution. This right here, very important. So I'm going to circle that. The half equivalence point, pH is equal to the pKa. You'll see that our equivalence point is 50 milliliters. So I needed to add 50 milliliters of the strong base to reach the equivalence point. Your half equivalence point would be when I add half of that. So right here, when I add 25 milliliters of that strong base, that's where we know where our half equivalence point is. So this is the half equivalence point. It's when you add less or half of the amount of base that it took to reach the equivalence point. So all of these sections are very important when you're considering a weak acid with a strong base or a weak base with a strong acid, that buffer region, that half equivalence point. Let's go ahead and look at the sample titration curve below, and then we'll get into more simple titration curves after this just by looking at some of them. So let's look at sample problem 19. So it looks just like that titration curve we did before. However, we do know that this is with a weak acid. We know that because there's a few reasons how we know that. Number one, our pH, we're starting off a little bit higher. That's one way we know this is a weak acid. We also know this is a weak acid because we see this buffer region, right? We see this chain or this resisting pH for quite a long period of time. We also know that this is a weak acid because we see the equivalence point is quite a bit higher than 7, okay? So, and there's chemistry that goes behind that, which I'm not going to get into in this video, I don't think. We'll do some more of the why the equivalence point is higher later on when we do some calculations. But let's go ahead and consider what's in the beaker at each of these different stages. So for A, when we're at 0 milliliters, right in the beginning, we're only going to have weak acid that's present. So I'm going to say we have some weak acid, and we have weak acid, but we have very, very, very little of that conjugate base, right? Because this is a relatively acidic solution, it has to have a lot more of that weak acid relative to its conjugate base. So what I'm going to do is I'm going to draw some ha-ha-has, right? So there's my weak acid. Looks like I drew 6 of them. 1, 2, sorry, not sorry. It's going to be a little hard to see. There's 4, 5, 6 of them. But I do have some dissociated weak acid there. So even though it doesn't dissociate a lot, you will have some weak acid there that is in fact dissociated. Notice this technically isn't a buffer to start off with. I didn't make a buffer yet. All I have is a weak acid. I can make a buffer by adding a strong acid to a weak or a strong base to a weak acid. And we're going to see how that happens as we progress through this. Here's my equilibrium reaction for a weak acid. So I have HA is in equilibrium with hydrogen ions and some of those right there. If I add hydroxide, so if I add my strong base to this weak acid, right, what's going to happen? Think Le Chatelier's principle. Those hydroxides are going to take away these to make water. If my hydrogen ion concentration is going down, this reaction is going to go in the forward direction. It's trying to compensate to make more of those hydrogen ions. And it does that by also creating more of its conjugate base. So we can make a buffer and increase the concentration of that conjugate base by adding a strong acid. A lot of people don't realize that you can make a buffer that way. You can make a buffer by having a weak acid and adding some salt that contains its conjugate base. Or you could also have a weak acid and add a little bit of a strong base. And that makes a buffer too. So as I add some strong base, like we said, we're going to start using up some of those protons that are in here. I'm still going to have more weak acid than I have conjugate base though. And that's because we didn't reach our half equivalence point here. Here's the half equivalence point. And this whole entire section is called our buffer region. So that's the buffer. At B, pH a little bit higher, but not too much. So my concentration of acid is actually higher than my concentration of the conjugate base. I only produced a little bit more conjugate base. So if I write how many of here are present, I'm going to draw 4 ha-ha-has, because I'm still going to have a lot of that weak acid that's present. I'm also going to have some more of that conjugate base. Okay, I'm going to increase that concentration of that conjugate base. So what I'm going to do is we have to remember that if I'm adding a strong base to this, we do also have a spectator here. So let's pretend that I have a spectator there. I'm just going to say sodium. And I still have a slightly acidic solution. So I'm still going to have a proton there. But notice how I increased the concentration of that conjugate base because those hydroxides are forcing that weak acid to dissociate according to Le Chatelier's principle. At part C, okay, at part C, this is where your concentration of the weak acid is equal to the concentration of the conjugate base. This is where the pH is equal to the pKa. Right? This is where you have your perfect buffer, because if I add some strong acid to this, it's going to resist the change in pH for a long period of time. And if I add some strong base, it's going to resist the change in pH for a long period of time. Let's say I'm here and I add some strong acid. That strong acid can't resist, or that buffer can't resist that change in pH for very long because it has too much acid to begin with. Okay. If I have here, if I'm at point D is not a great buffer because it doesn't resist that change in pH when more base is added. C is really the point where you have the best buffers, where you have equal amounts of weak acid to its conjugate base. So I'm going to eliminate spectators here. Like I said, I think it's a little bit easier to consider it this way. I'm going to draw 3 Ha's. And I'm going to draw 3 A- ones. just to show that that concentration is the same. That's a perfect buffer, because if I add acid to that, that acid is going to react with the conjugate base. If I add base to that, it's going to react with that weak acid. As I move up, so I'm still in that buffer region, but at this point, I have slightly more conjugate base than I have of that weak acid. So at this point, let's draw 2 ha-has, and I'll draw 4. 1, 2, 3, 4. That was definitely 5. Is it 1, 2, 3, 4, 5? I think it was 5. It's fine. You get the idea. Okay. I have a lot more of that conjugate base that's present at that particular point in time. We know that we have reached the equivalence point, and that's because all of that acid is now gone. So I have no more acid left. And I know that I have no acid left because if I keep adding base, there's no more protons to react with that. So if I ran out of protons, this is going to become basic very quickly. So when I'm at point E, all I have here is just some of that conjugate base, right? I have that conjugate base that's there. I'll just draw a couple of these present. So all I have at that point is A. I have no more acid because I'm changing the pH too quickly, and I don't have enough base. And this is because at this equivalence point, so this is the equivalence point, all your moles of acid is equal to your moles of base. They're totally equal to one another. So you don't have acid and you don't have base. Once you go past that equivalence point, though, you'll notice that you have some of that conjugate base, but you are going to have some hydroxide ions that are present. So in this beaker, I'm going to have some of these, but I'll also have a couple of hydroxides, and that's what's raising the pH. It is now a basic solution when I get it to that point. This is not the easiest thing in the world, right? But we got to just practice with this. College Board loves these titrations. They love pictures. They want you to compare pH versus pKa, which we've already done actually with Henderson Hasselbalch by looking at what happens to the pH when we alter that log of that base over acid ratio. You've done that already. We're just now applying it to titration curves. We're going to look at some very simple titration curves at this point. And looks like we have 1, 2, 3, 4, 5 more to look at. This won't take very long. Sometimes you might have titrations with polyprotic acid. And polyprotic, poly means many. And of course, protic means protons. So sometimes you might have a titration curve that shows a titration of many protons that are leaving that particular acid. And it's going to look something like this. So you'll see you have 3 equivalence points. You have 3 equivalence points. You have 1 equivalence point, 1 equivalence point. Looks like we have 2 equivalence points. And we have a 3rd equivalence point. Because I have 3 equivalence points, this must mean that this particular titration curve represents a triprotic acid. Triprotic means it has 3 protons. What could it be? Maybe it's phosphoric acid, right? Could be that because phosphoric acid has 3 protons. So this could easily represent something like that. What would it look like if I had, let's say, sulfuric acid? I probably would stop the graph right out about here because it would remove the first proton and then it would remove that second proton. So just beware that you might see a titration curve that looks something like this with many bumps, and that's just because you're removing consecutive hydrogen atoms. Let's take a look right here. So which line represents the weak acid? Now, unfortunately, yours is in black and white, so if you want to color code, you can. But the weak acid is represented by the orange line. And you can tell because not only is your pH a little bit higher, but you have this very nice buffer region that's present. So your strong acid is represented by the green line right there. I have a very, very, very low pH to start as it progresses, and then ultimately it changes very quickly. Which titration curve will have the higher equivalence point? Looks like for the green, my equivalence point is right at about 7 again. because this looks like it's for a strong acid with a strong base. For my orange, looks like my equivalence point's a little bit higher than that. We're going to say maybe at about 8.5 to 9. We're just kind of estimating. So your equivalence point is higher for the weak acid. Like I said, we'll get into why as we do more problems with this in class, but do note that that equivalence point is not the same. Here's a slightly different titration curve, and I looked at the answer key with this, and I do not agree with the answer key for this. So I am going off of my instincts on this one. And I feel that this is a reaction with a weak base. So we're starting off high here with a weak base and a weak acid. Here's why I think that. I think it's a weak base. Yes, the pH is very high, but notice how they labeled this buffer region. If you have a buffer region, it has to be a weak base, right? So that's why I'm thinking this is a weak base with a weak acid. Maybe I'm totally off here, but these are my feelings on it. So especially they labeled the half equivalence point, which I find interesting. So anyway, because they said this was a strong base with a weak acid. And I was like, strong bases won't have that buffer region. Anyway, so we said weak base plus a weak acid. What's the pH of the equivalence point? If I look at this equivalence point, and again, it looks like my equivalence point, somewhere about 8.5 to 9, we'll say. 8.5 to 9 again, somewhere around there. You don't have to be too specific about that. That's my estimation. What's the pH of the end point? So the end point would be where the reaction is totally over. So my end point looks like it's right at about, I don't know, like between 5.5, right? 5 to 6, somewhere right at about there. So about 5 to 6, somewhere around that region. What ions are present at point A? So if I have point A, all I would really have are just weak base ions. So I would have maybe some of my weak base. Now, if bases accept protons, I could have water here, and I'd have some BH plus 1 and some hydroxide. That's kind of the reaction for a base that's accepting a proton, because, of course, bases make hydroxide in solution. So that's how we could represent that. How does the pH, and this is another reason why I don't think this is a strong base, is because they talk about the pKb. pKbs will have very high, or the Kb for strong bases will be much greater than 1. So we wouldn't have that buffer region. Do you see where I'm getting at here? I do not agree with the strong base argument. I believe this is a weak base, because especially because it's mentioning pKb. pH of pKb. pH and pKb at point B. So it looks like the pH is a little bit higher than the pKb, right? So, and this means if the pH is higher, this means that I have to have more base that's present. And I do, because the pH is a little bit higher. It's above this half equivalence point. At point C, my pH would be lower than my pKb. Okay. And again, I would have a little bit more acid that's present at this point, since I'm adding, or I would have some more of that, at this point, I would have a little bit more of that conjugate acid. So once I have that conjugate acid, that pH is going to go down. So my pH is less than my pKb. And what's present at point D? I would have some weak acid. That's there. I would produce water, because of course, anytime I have a base with an acid, it makes water. And I'd also have some spectator ions. This is where I think they were trying to compare. This one is very clearly a weak acid and a weak base. Weak acid and a weak base. Again, I don't like that they compared, that they said that this was a strong base, only because of that buffer region. When I look at this, I see 2 slightly buffer regions, but I also see this pH is not quite that high and this pH is not quite that low. So tells me it's strong and or weak and weak. A represents the buffer region, because notice it's resisting that change in pH, and B represents the equivalence point. Now, something like this, I was just in a meeting last night, actually. You know, those meetings I do once a month. And somebody was saying, they're like, oh, they told their students there would never be a weak acid, weak base question on the exam. And she says, and I was proved a liar that year because there was a weak acid, weak base question. And one of the questions was asking, what's the pH at the equivalence point? And I wasn't sure how to figure that out because I had one answer. And this teacher who's been teaching AP chemistry for a very long time said you actually have to look at the Ka values and the Kb values. So we're going to do that problem very soon because I thought that was a great question. I want you to see how to kind of do a weak base with a weak acid because I don't want to be proved a liar at any point. Last one right here. Answer the questions given the titration curve below. So it says a 45 milliliter sample of 0.1 molar ammonium hydroxide, which is a weak base, is titrated with hydrofluoric, which is a weak acid. What volume of HF was used to neutralize the base? I don't have to do any work for this because it tells me in this titration curve what volume of HF was used. We're titrating it with HF, and we can tell that because my pH is starting off pretty high. So this must be the base. I'm titrating with acid because as I go across, my pH is going down. We know that we've neutralized that base when I get to that equivalence point right here, because this is where the moles of acid equals the moles of base. And if I go down, we could see that we've totally neutralized that base when I added 25 milliliters of that acid. And you'll see that once I go past that point, the pH drops quite a bit because, of course, you have a lot more acid that's present. Concentration of hydrofluoric. You do have to, in fact, calculate or do some stoichiometry here. So just like we were doing before, let's start off with 45 milliliters of the sodium hydroxide, or I'm sorry, ammonium hydroxide. 1,000 milliliters is in 1 liter. 1 liter of ammonium hydroxide contains 0.1 moles. And this is a 1-to-1 mole ratio, which is nice. So I will just let you know that. So this is not quite as long. And you find that you get 0.0045 moles of hydrofluoric acid. But we also know that I used 25 milliliters of hydrofluoric acid. So it's always moles per liter. If I know that based on this stoichiometry, I must have reacted 0.0045 moles, I'm going to divide that by 0.025 liters of hydrofluoric. And that gives me my concentration of 0.18. Again, the key to these is just getting practice, right? You got to do some stoichiometry sometimes. You got to look at the graph sometimes. This is what we're focusing on. We're putting it all together at this point. You now know just about everything about acids and bases that you need to know according to College Board. What indicator would be best for the titration? So it looks like this particular reaction, we want something that signals the equivalence point. And the equivalence point is somewhere about 9, right? About a pH of 9. So my best indicator would be thymol blue because that's also going to signal the endpoint at about a pH of 9, right? And that makes sense. So we'll say that thymol blue changes color closest to the pH of the equivalence point. And that's Unit 8. Those are your notes for Unit 8. We're going to do a lot of practice with this in class. We still got a couple more weeks to go. As always, if you have any questions, please let me know. I will see you in the next video, actually, which I think we're going to hop back to thermodynamics after this. And so I will see you back in Unit 6. Have a wonderful day. Bye.